right. So I'm Peter Weber. I'm Dean of the Graduate School, and I would like to welcome you all here. But first and foremost, I would like to thank the organizers of this conference, of this meeting, for the wonderful event. I know, Soren, you've been talking about this for many, many years. Is it decades? I know it's not many decades, but I know that you and you have been, ever since I've known you, you have been talking about this. So let me thank Soren in particular.
We want to build an institute. Join for Neumann Institute for Advanced Studies. So stay tuned.
And we'll come to that. So Soren asked me to say a few words, and so again, first of all, thank you for you guys organizing that. I thank you all for traveling from far and wide to come here. It's really great to welcome you to Brown here. But this evening, or this current session, is devoted to the graduate students, and so I'm really particularly pleased at how integral the graduate students are to this conference. And so I was thinking a little bit about Johnny von Neumann, and one of his trademarks is the wide spread of disciplines and his intellectual activities. And of course, you try, and you did a great job in including all these different disciplines in this conference: economics, physics, mathematics, computer science, biology. I caught a little bit of the discussion on evolution. And so it's a wide range of topics, and a wide range of fields that sort of come together in this conference. And so when I thought about this, it really reflects very nicely the intellectual, the content, the thinking of graduate education at Brown University. The way I like to think of it is that all our graduate students are sort of independent scholars and thinkers, and they create their own piece of science, of humanities research, and they've developed their own field. And one of the things when I became dean was to I was thinking hard about how can I get graduate students out of their box, out of their individual, small, narrowly defined disciplines, and how can I enable graduate students to be more broadly trained. And so with that in mind, I created this open graduate education system, which is, as many of you know, a scheme by which a doctoral student in any field can get a master's degree in any other field. And so this is sort of, in my mind, a uniquely Brown way of doing it, because for the undergraduates, we have the open curriculum. Or undergraduates, they can do whatever they want. They can create their own major, and as long as it makes sense, they can define their major. So very few do that, all right, but still they could if they wanted to. So our PhD students have the ability to gain expertise in a second field. And the way I kind of think about it is that in many places you define an interdisciplinary area, and then you say, oh, now I need an institute or a center in this particular interdisciplinary area. But you guys are smart mathematicians and computer scientists, and you can probably figure out better than I can how many interdisciplinary areas there might possibly be. And especially if you now define 3 areas, any 3, and so forth, you can propagate that, and you find that you will need an ever-increasing number of institutes and centers for ever stranger combinations of human knowledge. And so instead of doing that, this open graduate education that we defined is sort of crowdsourcing the whole thing, because we say, well, never mind what university administrators might think, we just let the students decide. And so by simply enabling students to define their field, we sort of crowdsource interdisciplinarity. And so here is a little chart that shows, this is a program that we started with the first cohort in 2012, and we are now we have admitted the cohort of 2015, so we have a grand total of 4 cohorts here. And you see the fields of the students and how the crowdsourcing in fact works. And so there in the inner circle are listed the doctoral programs of our open graduate education students, and on the outer circle are the master's program. So these people do a regular master's degree in some other field. And so you find some fantastic things here. And in particular, I think Soren, it very much would fit into how Johnny von Neumann would have thought about interdisciplinarity. So there are a lot of there are 2 chemistry students who do computer science. There is a computer science student who do mathematics. Those are the gray things over there. And so maybe those are fields that you would have thought about. But you also find that there is an economics student doing applied mathematics. And so our economists here in the audience will be pleased to see that economics students benefit from that too. There is also a neuroscience student doing applied mathematics, and a CLIP student, that's a cognitive, linguistic, and psychological sciences, doing computer science. And so you see students by throwing this wide open and say, students, we leave it up to you. You have a good idea. It needs to be a good idea. It needs to make some sense. There needs to be a system in there. But you have a good idea. We enable you to do that. The graduate school pays for the whole thing. And that is the university. And so now students come up with these fantastic combinations, and every one of them is actually based on a proposal where a student, for example, wrote why it is necessary for a philosopher to get a degree in applied mathematics. Maybe you also see, okay, there's an Egyptologist doing applied mathematics, and you say, what's that, right? But then you talk to the student, and it's a fantastic student in Egyptology, so he studies ancient Egyptian languages. But he wonders, well, how might that language have been spoken? And of course, now you need pattern recognitions, you need reconstruction from the alphabet, which you have, to the spoken language, and it's entirely non-trivial. And it requires a lot of applied mathematics. And so the student, when he first applied, I thought, well, this is not going to work. and so I told the student that, look, you first take some math classes and show me that you can pass these math classes. So the student did that and came back, applied a year later, and it's like, okay, I showed you that I can do it. And so then I said, okay, this is great, you're in. So this is a graduate education in a very interdisciplinary spirit, and I think this is something that you can only do at Brown University. I've talked about this at the AAU, the American Association for Universities. I talked to this about the Council of Graduate Schools. I talked to this to my Ivy Plus peers, and basically every institution finds that they can't do this because there are administrative barriers. These are the students in school of X, and I'm in the dean of Y, and over there is the school of something or else, and we can never get this worked out. But Brown, we are flexible, and I'm pleased to say that we are small enough to pull this off, and with that, I think we can offer our students, you here, opportunities that maybe you couldn't get at any other institution. So with that, let me thank you again for hosting this and for offering our students this great conference and insights and meeting wonderful people, visitors who come here to tell about terrific things. Thank you.
Thank you. So to continue this interdisciplinary spirit, we will have now a conversation with Professor Dyson. If you would like to, and please, graduate students, faculty, guests, ask questions. I have a few prepared that I'm going to ask because I spent some time with Professor Dyson to make sure that we record his recollection of this, priceless memories from those times. So I'm going to join you at the table. We'll have some water in case we need some. All right, the adventures of Gianni von Neumann at the Institute for Advanced Study in that golden era. So we agreed that one of the topics that is not very well known about Gianni's adventure there was focused on weather prediction and meteorology. And Gianni believed that by now we should be in charge of the weather. We can correct it, stop rain from happening, or make rain happen, all these things. But he was very interested in meteorology. And would you like to tell us a little bit about?
Yes, I should say, first of all, to make a complaint about the conference, that you didn't do pure mathematics. That pure mathematics was actually von Neumann's most passionate interest. And he spent at least half of his life doing pure mathematics, and that didn't appear on the program, which is in a way very sad.
Can I defend? There are only 4 days. He worked on so many areas. We promise the mathematics day, and I hope you come back.
Thank you. Good. I mean, it was for him, I think, the most important of all his activities, certainly the one in which he put his real passions into it. So anyhow, that said, now to talk about climate, and he gave a talk which I remember very vividly, in which, of course, he always talked with great confidence, and he said, look, there are only 2 possible states of the atmosphere. Either it's stable or it's unstable. And you can tell by looking at it which it is. And if it's stable, we can predict it. If it's unstable, we can control it. And that's what he actually believed and he actually proposed to do. His idea was if atmosphere was unstable, it meant that you could put on a small perturbation meaning a flight of airplanes with smoke generators just flying high up in the sky, changing the pattern of sunlight and shade would be sufficient. So that you could apply this small perturbation over a limited area and could move it from an unstable state to a stable state, and then it would be under your control. Now, he did not know about chaos, which had been actually discovered by Mary Cartwright about 10 years before. Mary Cartwright didn't talk to the meteorologists, so meteorologists weren't aware of it. Chaos had actually been invented in the wartime as a result of the development of high-powered radio transmitters. So it was discovered that these radio transmitters behaved badly, and the military, of course, blamed the manufacturers for manufacturing them wrong, but it was actually not the fault of the manufacturers, it was the fault of the equations. And the equation for radios, for a nonlinear radio amplifier, is inherently unstable, and it has these chaotic solutions which Mary Cartwright discovered. But von Neumann was totally unaware of all that. So, in point of fact, if you take an unstable atmosphere, it's almost always chaotic, which means if you move it slightly from one configuration to another, you only move it from one chaotic state to another, and your control is no better afterwards than it was before. So this whole program of von Neumann was totally illusory, but he was never aware of that. He always thought, I think right up to the end of his life, he thought that he would be able to control the weather in a fairly short time. He had roughly a 10-year horizon, and he thought by about 10 years from that time he was talking, which was 1952, I suppose, he would have the job done. And
yes, von Neumann. So how did you meet him? What was your first meeting with him?
I remember the first meeting very vividly because Dirac's kids were rushing around the table in the Institute common room. I walked into the Institute for Advanced Study, and immediately there were these 2 very rowdy kids who belonged to Dirac racing around the table in the common room, and this a very well-dressed gentleman standing looking rather bewildered, who turned out to be von Neumann. So I thought immediately, oh, this is the right kind of place for me.
Did you talk to him at that time?
Yes, and of course, I mean, he explained they weren't his kids, but... he was, of course, a very approachable and convivial character. I did not talk with him very much about mathematics. because he was at that time already completely involved with the computer. It was for him, it was absolutely the consuming activity to get this computer built. But he was very much interested in meteorology. So he invited all the best meteorologists that he could find, most of whom came from Norway. Norway has always been, of course, a great country for meteorology since they have such lousy weather. and they also had some very bright people. So there was Fjortoft and Eliasson, whom I remember very well, both of them Norwegian. And there was Charney, who was actually the leading meteorologist. His wife was Norwegian, so he actually had very good contacts there. And Charney was the leader of the meteorologists, and he was much more skeptical than von Neumann about this idea of climate control. Don't think Charney ever believed in that. And Charney did wonderful work just getting the equations of the atmosphere into a form where they could actually be handled on this very primitive computer. And after a long time, they finally decided that they better go to the ENIAC. The ENIAC was a computer that already existed in Philadelphia, the University of Pennsylvania, as von Neumann's machine didn't yet work. And they did the first weather predictions, and it actually took them just a little bit more than 24 hours to predict 24 hours ahead. So they were always falling just a little bit behind.
That computer affectionately known as the Joniac.
Ours was the Joniac. It was
Yes.
the one in the ENIAC actually worked.
In Philadelphia.
But of course, it was much slower. And it didn't have software. Von Neumann's invention was software. The electronic computer already existed, but what von Neumann added was software, which made the thing, of course, far more capable and far more flexible.
So when I ask you, thinking of today, we understand what a giant von Neumann is, despite the fact that he died at age 53. So I ask you if at that time you were aware of his stature, and you said you were enormously respectful of his work. Can you elaborate a little bit?
Yeah, well, I've known him, of course, from his pure mathematics. I was a pure mathematician myself, and so I studied his pure mathematical papers, which were absolutely brilliant. I mean, especially, of course, his invention of one things and two things. That was von Neumann's great contribution to pure mathematics. That he loved to think in abstract terms, and so he didn't use ordinary words. He called the two kinds of objects in set theory one things and two things, which, of course, nowadays we call classes and sets. And his brilliant idea, which was his main contribution, in fact, to the foundations of mathematics, was that you could actually have a consistent set theory with that two kinds of objects. Because the original set theory of Cantor had only one kind of set. So you talked about the set of all sets, and then you got into logical contradictions. So there was a huge crisis in mathematics when Russell posed this paradox that you could let X be the set of all sets, then does X belong to X? And no, that's not quite true. You have another set called Y. Y is the set of all sets that do not belong to themselves. And then the question is, does Y belong to itself? And that question has no answer. So you have a logical paradox. So this theory of set theory was in a state of total crisis. And the whole question whether mathematics was consistent, of course, was deeply troubling to the mathematicians at that time, particularly to Hilbert, who was the leading mathematician in the world. Von Neumann was a close friend of Hilbert. So von Neumann set himself that problem to try to straighten out mathematics from the bottom up. And so he did it with this system of axioms where you had both classes and sets. So you had the class of all sets, which was allowed, but the set of all sets was not allowed. The class of all classes was not allowed. And with that, you escaped all the contradictions, and you actually had a workable theory. And then a few years later, then Gödel used von Neumann's axioms to prove the Gödel incompleteness theorem that said mathematics could never be complete. And from there, of course, grew this whole new world of pure mathematics where we were free to invent our axioms.
So you heard him give 2 lectures. Can you tell us a little bit how he looked as a professor, von Neumann?
I didn't really know him as a professor. He was, of course, an extremely busy traveler. He was, the time when I knew him, he was already a member of the Atomic Energy Commission, which was running the nuclear enterprise in the United States. So he was deeply involved in the nuclear business, both the civilian and military. So he was spending at least half of his time in Washington. And then, of course, he was, when he was in Princeton, he was mostly involved in administration, dealing with the problems of the computer. And it was all completely alien territory for the Institute for Advanced Study. And the Institute for Advanced Study, of course, was a very snobbish institution with these elderly professors who had a great respect for each other and for themselves. And their code of ethics was sort of governed by formal politeness. And then von Neumann brought in all these young hooligans who were engineers with dirty fingers. And so there was a terrible culture clash. And von Neumann had to deal with all that. Of course, I was on the side of the hooligans. And
but you are telling that there was a very large percent of women scientists or students compared with this time.
Yes, that was true. It was, of course, a wonderful time just after World War II. I arrived there in 1948, so it was 3 years after the end of the war. Of course, it was a great time for women because during the war, the men had mostly been away fighting, and the women could get ahead in the academic world. And so, actually, that year when I came to Princeton as a member of the institute, there were 30% of us were women, and it's never been that high ever since. It's all been downhill, in spite of the fact we try very hard to get women as members. But it usually runs around 10 or 15% nowadays. It's sad.
Yes, indeed. We're making a lot of effort at Brown on the same front, so I think the time will come.
I blame the PhD system for it, just to a great extent. This is off the subject, but it happens to be a hobby horse of mine that the PhD system really discriminates against women. It uses up the best years of their lives in unprofitable study of things that they mostly don't need, and it just goes on far too long. And it's worse for women than for men because of the biological clock, which of course is inescapable. And so I find if we could just abolish the PhD or make it trivial, my solution to the problem is to give everybody a PhD at birth and get it over with.
There is support. There is support. So let's talk a little bit computation. This is a conference about computation. So you were talking about the bombs, the computation, the big computations required to envision the bombs, plan their design. Tell us a little bit.
Yes, well, of course, one of the big objectives of von Neumann in building the computer was to be able to design nuclear weapons. He had been at Los Alamos, and of course at Los Alamos, computers were mostly ladies, and they were working terribly hard just to do one implosion. Took about a month to run an implosion calculation just by hand with these very, very hard-working ladies. And von Neumann realized that you could do it electronically, it would go much faster and be much more humane. And so he organized what was called Project Matterhorn, which was a Princeton-based, essentially branch of Los Alamos. John Wheeler was very much involved with that. And so they ran computer calculations at night. So there was a night shift when everything was secret, when the hydrogen bomb people came and did their stuff. And then in the daytime you had the meteorologists, and they weren't supposed to talk to each other. Wow. Was it a...
Yeah, I did. I moved my... Sorry.
Anyway. So anyhow, it wasn't a bomb this time. So these people came at night and ran what was called the classical super. The classical super was Teller's original design for a hydrogen bomb, which in fact didn't work. And it took a long time to prove that it didn't work. So it was simply a big tank of liquid hydrogen, essentially, liquid deuterium, with a little bit of tritium at one end, and then a fission bomb. And so you exploded the fission bomb and hoped that the detonation wave would ignite the tritium, and the tritium would ignite the deuterium, and the thing would propagate. And there's a famous picture which Gamow drew of this classical super, which shows it's Teller trying to light a wet piece of rock with a match. And that's roughly speaking how well it worked. And so that these hydrogen bomb calculations were going on always at night. Julian Bigelow was, I think, one of the few people who was cleared for both parts of the operation, and so he was up day and night trying to get the machine to run. He was the chief engineer, and a great character. So in the daytime they did meteorology, and one other thing which they did, which we did not talk about today, I wish we had, it was Niels Baricelli. But Niels Baricelli was actually Norwegian also. He had an Italian name, but he came from Norway. And he did simulated evolution, which was quite amazing how much he managed to do. He did, so it was population biology done with little numerical organisms. So these were artificial creatures made up of numbers, which had the basic biological functions. They could reproduce, they could mate, they could become parasites, they could become predators and prey, and they could evolve. And he actually managed to simulate all this with a total memory of 40 kilobytes, which was quite amazing. That was 40 kilobytes was the total memory of that machine, and so everything we did had to be done inside 40 kilobytes. But he managed to do that, and he had these quite big populations of creatures. Each creature only specified by of the order of two or three bytes, and somehow he managed to simulate evolution very nicely, I thought absolutely brilliant piece of work. And von Neumann was very much interested in that. He saw a big future for this sort of synthetic biology, but it was totally forgotten. Baricelli went back to Norway after von Neumann died and got interested in virology, I think. And anyway, he didn't have a computer in Norway, so he dropped this simulated evolution. And nobody ever discovered his papers until about 40 years later after he died. And
Wow.
so there were many opportunities lost. We lost, I think, 3 big opportunities. First, computer science. I mean, we could have had a continuing activity in computer science at the Institute after von Neumann died. Second opportunity was, of course, meteorology, climate studies. We could have been 20 years ahead in climate studies, and we could have been ahead in simulated evolution, which could have been so three sort of scientific revolutions we missed because people were prejudiced and didn't like the engineers.
And tell what happened with the economists.
And there was a terrible clash just once when there was actually a memorandum written by the director of the Institute to von Neumann complaining that his engineers were taking too much sugar in their tea at tea time, and in future they were to have their tea separately in a different room. That was the level of the cultural dispute. So I'm sorry, you asked another question.
You mentioned that initially there was a School of Mathematics and School of Economics.
Oh yes, that was of course quite independent of von Neumann. Von Neumann was interested in economics, and so when they started the institute in 1929 or whatever it was, originally they had 3 schools. There was a School of Economics, and the School of History, and the School of Mathematics. And the School of Economics had actually some very famous people. Riefler was the one who actually built the house that we are now living in, and Winfield Riefler was his name. And then there was another economist called Stewart. And it happened just then when the Institute started that Roosevelt became president and started the New Deal, or that was even a little bit before. And so for the New Deal, he needed economists to run the country. And so these economists at the Institute all went to Washington and became big shots in the government. So the school collapsed. And that was unfortunate for us, but probably good for the country. And the New Deal on the whole worked pretty well. So anyway, so von Neumann did not work with those people. He became an economist independently through getting through who was interested in game theory, and then he got to know Morgenstern. Morgenstern taught him economics.
So maybe a last question from here so the audience can ask questions. So one comment that you made about his book, The Foundations of Quantum Mechanics, his famous book. I know I read about Turing, how excited Turing was when he got this as a present, because he was looking up to von Neumann, and was the best book he ever got as a present, and he was mesmerizing. So when I talked to you about this book, you were saying that the physicists not only that didn't read it, it was too abstract mathematically, and von Neumann was not regarded as his physics contributions were not through the book, from other things. So can you comment?
Yes, indeed, because I read that book, or like Turing, as a pure mathematician, and I mean, it's a wonderful piece of work. He took this extremely messy set of ideas which came out of quantum mechanics. I mean, the original quantum mechanics of Heisenberg and Schrödinger and Dirac was physically fantastic. It worked wonderfully well and explained experiments, but they didn't care about mathematics. And I mean, Hilbert was the great mathematician at the time. He complained bitterly to Dirac and told Dirac that your delta function can lead to all kinds of inconsistencies. And Dirac replied, "Did I get into inconsistencies?" But Dirac simply didn't care, and neither did Heisenberg, of course. They had no use for mathematical rigor. So what von Neumann wrote this book, The Foundations of Quantum Mechanics, in which he actually just made this whole subject mathematically respectable. And so it was a beautiful translation of the quantum mechanics into rigorous mathematical language, using, of course, Hilbert space, which Hilbert had invented for quite different purposes. And so quantum mechanics became, in fact, the theory of rings of operators in Hilbert space, which was something that I just enormously admired. But when I became a physicist myself, to my astonishment, I found out nobody read von Neumann and nobody even referred to him. If you looked through the whole physics literature, you'd never found von Neumann's name mentioned. And so physicists simply had no use for that kind of thing. It was a time when mathematics and physics were furthest apart, because mathematics at that time was dominated by Bourbaki. Bourbaki were these wonderfully abstract French mathematicians who believed that all mathematics had to be completely abstracted. So they took it as far away from the applications as possible. And so the physicists had absolutely no understanding of that. And so von Neumann got into physics in a quite different way. He had been trained as a chemical engineer. When he was a teenager, he already had 2 degrees, one in mathematics and one in chemical engineering. And so he knew about...
Because his father believed he will not be employable.
Yes.
Needed a back door.
Right. And so he had a very practical view of the world, which had nothing to do with physics at that time, but he understood chemistry, and actually came into explosives working for the United States Army as a chemist, and then understood that after all, if you really wanted to understand explosives, you better know some physics as well. And so he came into physics through that door. And then afterwards went to Los Alamos, of course, and got even deeper into physics.
So maybe the last question from me. He was very excited about computation. I think there was somewhere that he has an insane interest in computation. Did you witness some of those passionate things?
No, absolutely not. I never saw him working ever. And all I saw was either giving talks or just hanging around, and so I really know nothing about his methods of work.
Yeah, he wrote so many papers. I asked Marina this time, how in the world can he write those papers? You know, I'm agonizing, writing and rewriting many times. I'm sick and tired of myself. And Marina said that he would write in one pass a paper, and it will be just a few words that he would change for the secretary to type. So, superhuman. Anyway, so maybe some of you want to ask some questions. Please go ahead, please. Maybe.
Freeman, just curious if you ever heard him discuss game theory, or if you ever witnessed any of his interactions with Nash.
No, I didn't. And I mean,
He arrived right before the 3rd edition of Theory of Games, which
Yes, I honestly don't remember. It's just too long ago. And we got to know John Nash quite, but that was through the nursery school. He had kids in the nursery school the same time we did, but that had nothing to do with game theory.
Any other questions, students, colleagues?
So it seems that if he was here today, he might be upset that we cannot control the weather yet.
Yes.
Or maybe we'll never be able to control the weather. But what do you think he would be most impressed or excited by that he might not have, that exists now that he might not have predicted or might have predicted and would be excited that actually has come about?
Yeah, of course he was interested in everything, I can't speak for him at all, but I think he certainly would have been interested in astronomy, which is sort of now in a golden age, huge mysteries and huge new things being found all the time, and suddenly we have a little spacecraft and discovers 2,000 planets, which, I mean, the universe has opened up in a fantastic way, and just in the last 5 years. I'm sure he would have been excited by that, and of course it all has to do with big data. The fact that we can see the universe so clearly is simply due to the fact we can handle big data, and that's which is quite new. And so I think he obviously would be excited by that. And it's happening also in biology too, of course.
Good day. Since von Neumann had great contributions in both quantum mechanics, in physics, and in computation, in computer science, did you ever had a conversation with him about maybe his view on quantum computing as emerging discipline?
No, and of course, one thing von Neumann absolutely missed was the way the computer industry actually developed. I mean, he thought of computers right to the end of his life. He thought of computers as big, enormous machines belonging to government departments. I mean, and somebody asked him how many computers would the United States need, and he answered 18. He never imagined things getting cheap and small, which of course is the whole world is dominated by that, and so it's amazing. And of course, I never thought of that either, and I don't think anybody understood that's the way it could go. This idea that you could actually make computers for 3-year-olds and that everybody would have 3 or 4 of them, it was totally beyond his horizon. And I'm sure he would have found that extremely exciting. And yes?
He was right about 18, of course, because we have 18 computers now. It's Google, Netflix, everything else. The things we hold are not computers. They're just transparent terminals. So, but I was, von Neumann was very notorious about his quick mathematical wits and the way he would. There are many anecdotes about the fantastically quick reaction, how he could shoot down long-standing problems as that. So, do you have any anecdotes of this sort?
No, I don't. And I think Marina's book is probably the best place to look for those.
Yes, of course.
So you said that you knew John von Neumann's wife, one of the two, the second wife. You met her.
Yeah, she was, but that was after he died. She was married Eckhart, and they lived in La Jolla, and we got to know them extremely well. And so Clary was also, in her own right, a very interesting person. But I don't think we talked much about Johnny. It was not as far as I remember. We had more immediate things to talk about, and that was long past by then.
Please.
Do you have any insights into his musical preference?
Into
Music.
what was the question?
Do you have any insight into von Neumann's musical preferences?
No, absolutely not.
Well, as a matter of fact, I asked Marina this question when she was here, because the company recording all this were playing Beethoven at the beginning of the symposium, and one participant asked me, is this Johnny's favorite song? So I said, oh my God, I didn't ask Marina. So I asked, and she said that he was very interested in culture, but cannot remember a particular type of music he would have proposed for such a symposium.
Yeah, no, I couldn't answer that.
He sounds like a Wagner.
Please.
Yes.
So you mentioned he was incredibly interested in meteorology and he had ideas about how to control the weather, but then you mentioned chaos and how that complicates matters, and in your opinion, that we can't control the weather, right? That seems out of reach. That seems like his model must have been incomplete.
Yes, I mean, it's certainly not in the simple-minded way that he thought. I think, in fact, we probably can do a lot to control weather on the longer time scale, but not day to day in the way that he imagined. But you can certainly. I mean, Giulciani actually did a calculation, which was interesting. If you painted the Sahara black, that actually it would produce rainfall simply by making the surface much warmer. And the Sahara most of the time is cold. And so if you made the surface warm, the air would rise and you'd get then clouds and rainfall. So that you could probably change the climate just by painting it black. And of course, you can also improve the climate in cities by painting them white. And so that kind of intervention certainly can be made to work. It doesn't really require big computing. You have just to try it out and see. But as far as I know, none of the African countries have actually tried painting the desert black. But if you plant trees, it has a similar effect.
The task might seem easier if you rephrase it as influence.
Any other questions? Well, then let's thank Professor Dyson.
So thank you very much for inviting us.
So what's happening next is that we are going to show a video, John von Neumann, Mathematician and More. A beautiful movie by the American Mathematical Society, and it's about 50 minutes for the graduate students. Some of us will go to dinner, and we want to excuse ourselves. We have a bus for the speakers, but I'm hoping that the graduate student will enjoy the food, the dinner, and the movie. And Derek Aguiar promised to make sure that
No, he's going to.
Derek is in charge. In case the film doesn't work, he will fix everything. Thank you, Derek. Thank you so much.